Hey everyone. I am just going to come out and say that it's been a really tough week for me. My dad passed away this week, and I did not have the energy to look over a new episode of Pale Blue Pod. So I'm sorry, but it's a rerun this week, and I'm revisiting one of my favorite episodes from my time with Corinne. And also, my dad was a medievalist. He studied medieval literature, and when I got into astro stuff, he was always really excited about, the first astronomers like Kepler and Brahe and Galileo. So this is the Kepler episode where I talk about my favorite mission from NASA ever, the Kepler spacecraft, and its namesake, Johannes Kepler, a little bit in honor of my dad. There's going to be a new episode next week because I wanted to put a specific episode out for Cinco de Mayo, but I'm just going to take the time that I need, friends, and I hope that you're okay with that. So enjoy Kepler. I certainly have. Welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
How sweet. It's true. We're here. I'm Corinne Caputo, a writer and funny person and friend to the universe.
Yeah, you are. And a friend to me. Hi, everyone. Yes. I'm Dr. Moiya McTier. I'm an astrophysicist, a folklorist, and a friend to the universe. I tell the universe even when I'm having a bad day. Like I'm honest to the universe.
That's true
how
friend.
Close we are.
Yeah, That is the measure of a true friend.
Yes, because not every day is going to be the best, and your true friends are there for you no matter what. Today, though, we're having a pretty nice day because we are out on the water. We're in one of those cute little foot pedal boats on a lake with a bunch of swans, and the water is crystal clear, and these swans are beautiful. Even though they're loud. They get loud a little bit. We're gonna speak when they're not being that loud.
Swans are way bigger than you think they are. Or than I think they are.
Yeah, I was surprised. I didn't realize they would be this large.
Yep. Yeah, my favorite TV show, Vanderpump Rules on Bravo. Lisa Vanderpump owns some swans. And in one episode, she takes it to the restaurant because she was on the way to the vet, I think.
Okay, I was wondering where that would go.
Anyway, she's holding it in a way that I was like, that swan is 4 times as big as I thought swans were.
Maybe she's just 4 times as weak as you think she is.
Yeah, and also she might be very small, and I don't know. But something was off with the scale. No one was right.
Well, these swans on this lake are huge, surprisingly so. And the reason that I decided to bring you here to this lake to record this episode, I think will become clearer later. But today we're talking about one of my favorite things. This is, we've covered a few observatories / telescopes before now. This is without a doubt my favorite spacecraft mission.
Oh, I love it.
If you've been paying attention to all of our episodes of Pale Blue Pod, you'll know I'm a transit photometry girly. I am in love with that method of finding exoplanets, and the most successful space-based mission for mission in general. The most successful mission for finding exoplanets using that method so far has been the Kepler mission with the Kepler spacecraft, and that's what we're talking about today.
Yay!
Yay! Corinne, how much do you know or remember about what we've said about Kepler?
Nothing off my head, but that doesn't mean I don't know it. It'll probably just be familiar, as we say. But yeah, Kepler, to me, one of the most famous words in space.
Yes, named after one of the most famous scientists, so it has both of those things going for it. Is there anything you really want to know about Kepler, the Kepler spacecraft by the end of this episode?
Ooh, that's a good question. I want to know why it's your favorite.
Okay, we'll come to that. Well, I want to talk about what was going on in transit photometry before Kepler, because though it is my favorite, it was not the first. It's not even the only transit photometry space mission that we sent. And so I wanted to look into the history. I didn't realize where it started. Where do you think the idea of looking for transits in front of planets in front of stars started? How long ago?
Probably earlier than I think.
Yeah.
Or actually what I mean is by that is more recent than I think.
Okay, that's the opposite. All right.
Yeah. Because I think I tend to swing too hard in one of the directions, but I don't know when we started thinking about other planets beyond like our solar system, our stars, our etc.
Yeah. In folklore, we were thinking about it for a long time. In science, we were thinking about it probably starting in the 15 or 1600s, which is around the time that we got scientific about studying transits, although people had been able to observe transits for a very long time. It started with studying the transits of Mercury and Venus, actually. So within our own solar system, just looking at the planets that are between us and the sun. And it was actually one of those transits of Venus that helped us calculate the distance between the Earth and the sun. We knew it in proportions, but we didn't know what the absolute distance was until we saw and timed that transit.
Amazing.
But the first known scientific transit observation, meaning like people expected that it was going to happen and they used scientific instruments to measure stuff during this transit, was in 1631 by, I'm assuming, a Frenchman named Pierre Gassendi. And he was looking at Mercury as it passed in front of the sun. And that was a transit that was imprecisely predicted by Kepler. Not inaccurately, just imprecisely.
I'll take it.
There was a question about the difference between accuracy and precision when I took the physics GRE, and so I now always like to really think about that distinction, because he did get the right time frame. It was just there were error bars, and so Pierre Gassendi was able to observe the transit of Mercury in the time frame that Kepler predicted. But even earlier than that, there's this star called Algol. Algol, and it has been known throughout history to be variable. It gets dimmer and brighter over time. Noticeable before telescopes, but in the 1700s, after telescopes were invented, a man named John Goodricke measured its period. How long does it take it to go through a dim, bright cycle? And wrote that the variability was probably caused by, quote, the interposition of a large body revolving around Algol. Or it could be due to its own motion if there are spots on this star, just like we know there are spots on our sun, because people had been studying star spots or sunspots for about 100 years at that point. He then made a very important caveat for a scientist to make. He said, quote, but the intention of this paper is to communicate facts, not conjectures. And so he didn't want other people to believe that he was claiming for sure, oh, yes, there's like another planet going around this. It was just one potential idea. That idea was hypothesized around the same time, though, by, I think, probably a peer of his named Edward Pigott. Great name.
Yeah.
And he also was like, yeah, maybe there's a planet or something in front of this star. Because a few things needed to be in place for us to start thinking about planets around other stars. First, we needed to realize that we were ourselves a planet around the sun.
Exactly.
And it took a long time for the, at least Western scientific community to accept that. So that had to happen first. And then people tried to look for transits. They have ideas about different variable stars potentially having transits in front of them. They try to, or they think, someone thinks in the 1800s that they have detected a transit around a distant star called Beta Pictoris. But it seems that those were all unsuccessful. Flash forward to 1992, so a couple hundred years.
I was alive.
Yes, I was not.
Crazy, Moiya.
I know.
I was holding down the fort.
You were. I'm glad. I feel safe knowing that you were there in 1992.
I was in the room when they did this discovery.
You sure were.
I was right there.
So in 1992, Corinne and the other scientists in this mission detected the first exoplanet. It was detected using the radial velocity method. We have a whole episode about the different methods to detect exoplanets. So if you haven't listened to that, go back, because I'm not going to go over what the radial velocity method is in detail, but essentially you're looking for the slight motion in a star caused by the gravitational influence of a planet as it goes around. The first planet found around a real type of star that was fusing hydrogen in its core, that was in 1995, the year I was born. And I like to say that I've never lived in a world where we didn't know there were exoplanets.
I love that. Is such a romantic thing.
I know.
To think. I love it.
I know. The very first exoplanet scientist professor who was born after the discovery of exoplanets. She just got her first professorship.
Oh, fun.
Mm-hmm.
Wow.
Yeah, love that. But it wasn't until 1999 that we saw a planet transiting in front of a star that was not our sun. It was HD 209458b. It was a hot gas giant. It was discovered initially with the radial velocity method earlier that year in 1999, but later two teams separately observed the planet's transit. One team was led by Gregory Henry at Tennessee State University, and one was led by a grad student at Harvard named Dave Charbonneau, and he used a little ground-based telescope called STARE in Boulder, Colorado. And Dave Charbonneau was the professor who oversaw my thesis class, my undergrad thesis class. I handed him my thesis to submit it. I think I've told this story on the pod before, but I wrapped my thesis up, I swaddled it like a little baby, and I made this. Dave Charbonneau is so tall. He's like 6'3", 6'4", I don't know, he's giant, and he's Canadian, so he's very quiet. And he's pretty intimidating if you don't realize that he's not. And so I made him pose with me like I had just birthed this baby and he was like my dad. And this was now his little paper grandchild that I was turning over to him. So that was one of the people who detected the first transiting planet. Really cool. But it wasn't until 2002, 3 years later, that the first planet was discovered using the transit method, not just detected. And that planet, we call it OGLE, OGLE, TR 56b. We call it that because it was discovered by the OGLE project, which was a Polish survey to study variable stars. And before we realized how common exoplanets were in the galaxy, a lot of these stars that had periodic dips in their brightness, we thought that they were, we lumped them all together. We now understand that there are some stars that are inherently variable, Cepheid variables, for example, like some process inside of them makes them get brighter and dimmer over time. But a lot of what they thought were variable stars were actually just stars with planets passing in front of them. So this was the first to be detected that way. And then in 2006, the French Space Agency launched a satellite called CoRoT. It's a doubly awful acronym because it stands for convection, rotation, and planetary transits.
We dropped the P.
We dropped a lot.
Yeah.
We dropped a lot in there.
Every time we do one of these where it's like an acronym that doesn't quite fit, my mind is blown because as a kid learning what acronyms are in school, I'm like, there are rules to this. I did not know we could be this flexible with it. That would have changed a lot for me.
Well, I guess it's a good thing to learn.
Yeah.
A new avenue of
you
flexibility,
can bend
maybe?
the rules. I do believe in learning the rules so that you can bend them, but...
Yes. And also learning how other really official people have bent the rules beyond recognition.
Yes.
That's 2006. This is all pre-Kepler, which I'll tell you launched in 2009. But, of course, the road to getting Kepler launched was much longer than just those 3 years. This goes back to the 1980s, and the star of this little prequel story is a staff scientist, a research scientist at NASA Ames named William J. Barucki. He started advocating for a space mission to detect small rocky planets in 1984. We had done some work trying to detect planets from the ground, but that's really only going to be good for big planets that have very noticeable high signal-to-noise effects on the data. These small rocky planets aren't going to have a huge signal-to-noise ratio, meaning their signal might be so small that it is hidden by the noise and static of the detectors. If we can get something in space above the noisiness of the atmosphere, above all the aberration of the water, especially in our atmosphere, then we'd have a better view and our noise level would be lower, so maybe these small signals could rise above them. He submitted a proposal, his first proposal, to NASA for one of these space-based missions in 1992. He got rejected. Boom. He submitted again, I think in 1994, got rejected. Again in 1996, got rejected. He got rejected a total of 4 times before he was finally approved for this mission in 2001.
So I don't know if you have any insight into that, but do you have to like edit the proposal at all between submissions? Like, do you have to change the mission of it based on feedback?
They do give feedback, and it's a good idea to adjust, but also sometimes these missions, it's not always a fault in the mission that leads to a rejection. Sometimes they just have other things that they need to prioritize. Yeah.
Fair.
So I think it was in 1996 that he changed the name of the mission to Kepler to honor Johannes Kepler. I'm sure other smaller or bigger changes were made along the way, but it was finally accepted on the 5th try.
On the 5th try. 5th try's the charm.
Yep, that's what they say. So he got the funding in 2001, and he served as the PI, or the principal investigator, on the Kepler mission until he retired in 2015 after something like 53 years of service to the astronomy community at NASA specifically. The telescope seems to have just gone forward. The development of it seems to have gone forward without much of a hitch, at least not much of a public hitch that I could find in front of payrolls. But the telescope itself was designed by NASA Jet Propulsion Laboratory and Ball Aerospace. We can boo Ball Aerospace because of their connection to the military-industrial complex. We can boo Ball Aerospace. And also because they will never pay me anything. And I would not accept their money, and they would not want to pay me any money, so boo. The project was delayed a couple of times, once for like 8 months and another time for a handful of months, mostly because of NASA budget cuts that started around 2006. How much do you think it cost to build the Kepler spacecraft, Corinne? This is in like 2008 money.
2008? Like $500 million.
Wow, that's
because today I would say it would take $1 billion, and I think all money before 2020 was half as valuable as it is today.
Or twice as
valuable.
Yeah.
So, yeah.
Corinne, yeah, your instinct is so good. It's a little bit more. It's $600 million.
Okay.
Very, very close.
Very on point. Very close. Okay.
Good for you. Your former experience as a billionaire really paid off.
I know what things cost.
It launched on March 7th, 2009, and during its mission, it was operated by the Laboratory for Atmospheric and Space Physics at the University of Colorado, and the data was sent to the Kepler Data Management Center, or the Kepler DMC, which is located at the Space Telescope Science Institute in Baltimore on Johns Hopkins University's campus, or just off of its campus. Kepler's a big boy. It's how much do you think it weighs?
Ooh, that's a tough one. I don't know if I have an answer for that. I would say 1 ton.
Yes.
I was either going to say 50 pounds or 1 ton.
50 pounds! It would be the dream of every
As if those two numbers are close together at all.
No, I appreciate a bimodal distribution. It's either tiny or huge. 50 pounds would be a dream weight for anyone designing a space mission. Yeah. A lot of stuff has to like come off.
Yeah. It's like 10 grand or something a pound to launch in space.
Yeah. It weighs 2,291 pounds.
Wow.
When you look at it, it does kind of look like a golden tube of lipstick wearing solar panels as an open coat, or like an open vest coat. That can you look up a picture and confirm, please?
Yep. Okay, let's see. A golden tube of lipstick. Yes, wearing solar panel. Yeah, that's perfect.
Thank you.
That is perfect. There should be some kind of like, I don't know, Clinique, Kepler combo.
Oh.
Because that's exactly what Clinique's Black Honey Lip something looks like.
Oh. Amazing. The next talk I give about Kepler, I'm so going to do a side-by-side of that.
Yes, you have to. There was a space class I taught to kids during COVID, like virtually, and I just compared meteors to potatoes, and I thought it was the funniest thing I've ever done. They didn't get it.
That's hilarious.
Not that they didn't get it, but it was like teaching a virtual class to children. You're like, I don't actually know how this is getting received, but I thought it was pretty funny.
Well, I would have loved that.
I'll send you the slides.
Thanks. The mirror, there's a primary mirror, and then there's a mirror for like the main instrument, because there's one single instrument on Kepler, and then it's surrounded by a spacecraft. But the primary mirror that sends the light to the instrument is about 4.5 feet across. I think it's 1.3 meters for our international listeners. And that single primary mirror directs light to an instrument that's essentially just a camera. Kepler is basically just a camera that can look at a field of view and count how many photons it gets from different parts of that field.
Sure.
Fair, yeah. It primarily operates in the optical. It observes from 430 to 890 nanometers, so in the optical, but into the near infrared. We, our human eyes, cannot see at 890 nanometers. And the instrument provides what we call time series photometry data. So it gives us an amount of brightness at different snapshots in time for individual stars in its field of view, but also at the pixel level. And each pixel can have, like thousands of stars in it.
Yeah.
Yeah, it's a cool little instrument. It was designed to monitor about 100,000 main sequence stars. Main sequence stars are the ones that are actively fusing elements in their cores. And it observed a patch of sky, a single patch of sky that was about 12 by 12 degrees, so like 150 square degrees. For reference, the moon, a full moon, covers about half a degree.
Okay.
So they were observing a pretty big patch of the sky. In that patch of sky kind of straddled the line between the constellation Lyra and the constellation Cygnus. And Cygnus is the Swan, which is why I brought us to a swan lake.
Aww.
Yes. So it was supposed to observe about 100,000 stars. It ended up observing 530,506 stars in its field of view.
Many.
So many. It told us also a lot about those stars, but I'll get to that in the discoveries section. It orbits the sun. It does not orbit the Earth. And it trails slightly, ever so slightly behind the Earth with its own period of 372.5 days. It should kind of intersect with Earth, not collide with Earth, but intersect with our orbit every 61 years. And so like every 30 years, we'll be on opposite sides of the sun.
Aww.
Which is so cute. It was designed with 4 wheels on it to turn Kepler every 90 days so that it could stay staring at that single patch of sky as it orbited the sun. And when you get data from Kepler, it was arranged into 90-day batches or 90-day cycles, as they called them, because as it was turning, it would send down the data to the data management center.
Every 90 days.
Every 90 days. Yeah, like clockwork. For 4 years, Kepler stared at that patch of sky and did its little roly-poly as it went around the sun and sent us. It was like it was such a consistent.
I know. I'm like, that would be such a bad job for me. Like, sit there and look at that.
You're right. Those are the types of jobs that are perfect for robots.
Yeah.
Stare, look at that, count precisely, and tell me an exact number at the end. Not, write a song for me that sounds like The Weeknd. That is not what robots are for. So I did say for 4 years. Yeah. Kepler did that. But the entire mission that was proposed by William J. Barucki lasted 9 years, Corinne. So what happened after those first 4 years? Well, in July of 2012, one of those 4 stabilizing wheels broke. No. That's fine, because we build in a lot of redundancy to our spacecraft. So with 3 wheels, it could still function as designed. But another wheel broke in May of 2013.
No.
After that second wheel broke, Kepler was no longer able to stabilize itself and stare at that patch of sky in Cygnus. And I think for some other missions, we might have been like, oh, okay, well, let's just retire it. But it still had fuel left. It still had the ability to observe. And so NASA put out a call to the public on how they could, adapt this mission given its new constraints. And people sent in recommendations. A new mission was approved almost exactly a year later in May of 2014, and it was pretty much entirely led by guest investigators. So instead of just William Barucki being the principal investigator on this mission, it was now much more of a collaboration. The way that they changed it was that instead of staring at one patch of sky, the telescope was allowed to roll as it orbited the sun more continuously. And so it was always facing away from the sun, and that was balanced by the 2 remaining reaction wheels and the solar wind coming from the sun, this pressure of charged particles coming. And together they were able to always keep Kepler pointing away from the sun and observing patches along the ecliptic, which is the path that the sun seems to take along the course of a year. It observed 20 different patches of sky along the ecliptic over four-ish years. It wasn't perfect. I'd say there are definitely pros and cons to this new iteration of the Kepler mission, which they called K2. You needed to develop new processing pipelines that took the raw data from the telescope and turned it into something that scientists could readily use. You also needed to be more careful of the noise in the machine because the telescope wasn't staring at the patches of sky for a long time. The noise levels were higher because one cool thing about observing is that if you observe a patch of sky for more time, you collect more photons and your error, essentially your uncertainty in your measurement goes down. Mm-hmm. But they weren't staring at these patches for 4 years. They were staring at them for a few months. So the noise was way higher in K2. And they could only confirm short period planets with K2 because you have to be able to see at least it's better to see 2. You want to see 2 transits so you can measure the period. But in the Cygnus field of view, you could see any planet that had a period less than 4 years. But for K2, when you're looking all around the ecliptic, you only have a couple months. And, most planets have longer periods than that. Mm-hmm. But there are some good things. It let us see if the statistics of that Cygnus patch were the same as in other parts of the galaxy. And it seems, probably, especially if you're accounting for different directions in the galaxy having different numbers and types of stars. Ultimately, though, the K2 mission it's like a consolation that we got after the main thing went down. All in all, Kepler and K2 collected 678 gigabytes of data. They have data for full pixels as well as individual stars' light curves. They also have temperatures, radii or sizes, and colors in different wavelengths for each of the stars that it observed, over 500,000 of them. And it used 3.12 gallons of fuel in 9 years because it got a lot of solar power.
Oh,
because of that solar panel open vest. Yeah,
climate friendly queen.
Mm-hmm. Love to see it. Kepler was meant to last 3 years. It lasted more than 9.5. Thousands of papers were published using Kepler data. Almost 3,000 had been published using Kepler data by the time it retired officially in 2018. It found its first planets within a month, but the data was proprietary, and the team didn't publish their results for a year. And I have heard some insider tea here. I've heard some less than stellar whisperings about how kind of cutthroat the Kepler collaboration was. And it seems like there was this culture of really hoarding your data and being really afraid that people were going to scoop you because this was a brand new field. And even though the Kepler mission, was designed not to find individual planets, but to get a statistical understanding of exoplanet populations, people were really excited about those individual findings.
Yeah.
And so they didn't publish for a year, and I'm pretty sure a lot of people had to go to therapy because of their work in this collaboration.
This is why we shouldn't try to achieve things.
That's one thing you can take from it.
No, I kid.
I found this quote. There was a review of Kepler's discoveries and a review of the history of the mission. And this author said that the whole Kepler mission was characterized by, quote, a tension between the primary mission of Kepler to conduct a statistical census and the prestige and newsworthiness of discoveries of individual planets and planetary systems. There was constantly that tension there. Before retirement in 2018, they confirmed 2,662 planets. At the time, that was like at least 3/4 of all the planets that we had discovered. They observed 61 supernovae, which is cool. That wasn't one of their goals for the mission. And they had a few big, groundbreaking conceptual results. The first was that planets aren't rare and they actually outnumber stars. We had no idea how common planets were. We had no idea how common, especially Earth-like planets were. And within literally a week of turning on Kepler and like getting its focus right, they found dozens of planets. So
that must have felt crazy.
Right? I can't imagine what it was like in that. I mean, I can. I was born there. But I can't imagine what it was like in those rooms to see this data come through and like get it analyzed and see just planet after planet pop up, different types of planets too. Because that's one of the next things they found was that planets are actually very diverse. And we are lucky enough to see that in our own solar system. We see rocky bodies, gassy bodies, icy bodies. But we didn't know if we were the norm or the exception. And what we found was that there are a bunch of different types of planets, although most of the planets that Kepler confirmed are what we call super Earths or mini Neptunes in this size region between Earth and Neptune. They also found that small planets are more common than they thought. Like most of the planets in our solar system are pretty big, or at least they seem to dominate our solar system. The initial findings from Kepler were that between 20 and 50% of stars should have a rocky planet, specifically a rocky planet, in the habitable zone of that star. Which is a huge result.
Yeah.
This is after like Frank Drake made the Drake equation and estimated the number of habitable or communicating intelligent civilizations. This was one of the things that they really needed to know in the Drake equation to constrain that number is how many planets there are. So this is all happening in the 20 teens. Oh, so cool. I was around when this was happening. They also realized not just the planets are diverse, but that systems themselves are diverse. They can orbit multiple types of stars. They can have lots of planets that are really close into their stars. We realized that Jupiters can exist in all parts of the solar system, not just the outer one. You can find them in the middle. You can find them essentially touching their stars. And because it's impossible to study planets without studying their stars, Kepler provided years of photometry data for more than 500 million stars, even stars that didn't have planets around them. So all of the exoplanet people were like, oh, I don't care about those stars. But all the stars people were like, you have temperatures, you have colors, you have estimated radiuses, like you have a lot of information over 4 years of these stars, because that was uncommon in stellar surveys. You would usually only get like a very short observation of stars if you were doing a survey of the whole sky. Kepler was one of the first photometric surveys that stared at a specific patch for a long time. So those are its big conceptual findings. I have a list of some of the most notable planets that it has found, and I want to tell you about them in a little game for President's Day. Because if you're listening to this episode on the day it comes out, Happy President's Day, y'all.
Day, everyone. Oh, I'm so excited.
And so I'm going to tell you, Corinne, about an exoplanet that Kepler discovered. I'm going to give you some of its characteristics, and then I want you to tell me who you would want to make the president of this exoplanet. And it can be a reward or a punishment.
Yes. Okay, good. Good.
This is going in order of when these planets were found. So let's start in 2011, where we discovered Kepler 16b. This was the first exoplanet found orbiting 2 stars. And actually only a dozen of all of the Kepler planets, there are almost 3,000 of them, orbit a close binary star system where it's like one planet orbiting outside of 2 central stars. But we expect that those systems should be fairly common because most stars are born in pairs or triples or whatever. The planet itself is about the size of Saturn, but we don't know if it has rings. Okay. Maybe it does. It orbits every 230 days, so it's outside the habitable zone, making Kepler 16b cold, gassy, and far away from 2 bright spots that it can't help but stay bound to.
Feels like a curse.
It does, yeah.
Who needs to get cursed? Well, the first thing that came to mind before I thought about the curse was Elizabeth Olsen, because her older sisters, 2 twins, even more, or I don't know if they're more famous than her now, but Mary-Kate and Ashley Olsen, huge stars as she was growing up.
Yes.
So I'm going to stick with that.
Okay. I love that reasoning.
And then the Nepo baby of it all, you can't really escape that.
Do you think of her as a cold, gassy person?
No. I actually love her smile and face.
Oh, great. So she's not being put there as punishment. Maybe she's being put there in the hopes
she's going to turn it around.
She can brighten it up.
She's going to turn this around.
Is she the Scarlet Witch?
Yes, she's WandaVision.
Okay, she is WandaVision. Okay.
Obviously, my Marvel knowledge is showing.
Well, maybe she can use her powers or whatever.
She's got friends now.
Yeah.
She can get out of this.
Okay. So Elizabeth Olsen?
Yes.
For Kepler 16b. Let's make that campaign poster. Elizabeth Olsen for president of Kepler 16b. Excellent. Thank you for that. I'm sure the campaign will go well. But 2011 is a double election year. So again, in 2011, we found Kepler 22b. This is the first planet found in the habitable zone of a sun-like star, but it is not Earth-like because it's about 2.5 times bigger than Earth. So it's probably a gaseous world. Although some models implied that it might be a watery world. So let's just say that it's very humid. It orbits every 290 days, and the star is like the sun, so it's closer in and warmer. So let's say that this is just a hot, humid swamp world.
Ugh, that sounds awful.
Yeah, who should its president be?
Okay, this is not exactly a person, but you know the bit about, like, Florida Man?
Yes.
So this kind of sounds like Florida to me, or my limited experience with Florida. Sorry to our Floridians. But I really think Florida men would thrive here. Yes,
I love having like a folkloric legend as a presidential candidate. Because, you know, honestly, better than some presidential candidates I've seen.
Most, actually. But listeners, if you don't know what Florida Man is, a fun thing to do is just Google Florida Man followed by your birthday and then read whatever news headline comes up, because there's always one.
Oh, well, you know we have to do it. You know we have to do it live.
Okay, mine is Florida Man makes beer run with large gator in hand.
With large, I like to think that he was going to share with the gator.
Yeah.
The first ones are sad and gross. So let's skip and say Florida man arrested after argument over cheesecake. 'Cause honestly, relatable.
Yeah, same. We should be fighting about that.
And that's who I would want to be my president on Kepler 22b. I will fight for your cheesecake.
Yes, exactly.
Great job. Thank you for that. Now we're not having another election until 2013. Here we have to elect the president of Kepler 37b, which has the distinct honor of being the smallest planet found by Kepler. It is smaller than Mercury, only like 0.3 times the size of Earth. So small. It orbits its sun-like star every 13 days. So it is smaller than Mercury. It is closer in than Mercury. It is hot and very small. It's a planet with a Napoleon complex, I think.
Yeah. Okay. Who has one of those these days?
Yeah. Who needs to be cut down to size?
I'm trying to think of small celebrities. Like Tom Cruise. But I think this should be more of a punishment planet.
I agree.
Because I kind of like being stuck, like you're stuck in something small and time is moving quickly and you can't really do much about it. Maybe Trump.
Yeah. Yep. Honestly, yes. Can we
go
just
over there.
send him there? He's never committed any crimes or broken the Constitution of Kepler 37b, so
yeah,
he
just
can
start
go
over.
run there.
Wouldn't you want that? What if we offered you the deal of a lifetime where you can just completely start over and you would be the immediate king of the planet?
He would take that.
I think
probably
he should
so
take that
fast.
deal.
Yeah, that's a good one. Just send him over there. Gross. Sorry. Also, in 2013, we have two planets, Kepler 62e and 62f. These are the fourth and fifth planets away from their star. Because if I haven't explained it before, the naming convention for exoplanets is that it's Kepler or Ogle or Tess or whatever, which is the mission that found it, and then the number, and then the star is always that number, or it's A, and so the first planet is B, and then C, and then D.
I can get on board with that naming convention. That makes sense.
Except I don't know if it's the order that they were discovered in or the order from the star. Ooh. Usually that's the same thing because we tend to find closer in planets first, but not always. And I think there are probably some situations where it could be flipped.
What was that scale we talked about, I feel like in one of our earliest episodes, where they didn't realize things actually got smaller than that or something?
Oh,
so it like became, they tacked it onto the like negatives essentially?
The magnitude system for the brightness of objects. Yeah, where we were like, oh, well, what we can see, the dimmest thing we can see is the bottom. There's nothing dimmer than that. And then we had to go negative.
Yep.
Also, it's backwards, so like a lower number is bright.
Oh, because it's measuring the dimness.
There's no...
If that makes sense.
It's not that logical.
It briefly made sense, and then I lost it.
No, don't try to make Hipparchus's magnitude scale make sense. It doesn't. It is the bane of every burgeoning astronomer. But we have here Kepler 62e and 62f. So I'm saying this is a two-planet empire. They are likely water worlds based on models that we've run with information like the size of the planet, its mass, and how bright it is, because water, for example, is brighter. It's more reflective than dirt. So there are these things we can combine to get that model to tell us this is likely two worlds covered in oceans. It's a 5-planet system, as far as we can tell, orbiting a K-type star, which means it's dimmer than the sun. It's actually much dimmer than the sun because it's kind of an old system. Okay. Planet E orbits every 122 days. F orbits every 267 days. Both of them are in the habitable zone of their star. And if you do the math between those two periods, you'll see that they're almost in a 2-to-1 resonance. Planet E will be able to do a little bit more than 2 orbits every time Planet F makes 1 orbit. So they should spend a lot of their time kind of close together, which is nice for a 2-planet empire. Okay. But they will sometimes be far apart, which is scary for a 2-planet empire.
That would feel scary. Okay. As soon as you said Waterworld, I thought James Cameron, director of Titanic and Avatar: The Way of Water. Because he seems completely obsessed with water in these interviews in a way that I cannot relate to. And second, when they're far apart, that's kind of like me and the world asking him, when is Avatar coming out again? Why did we wait 12 years between Avatars? Where are you? But we come back together.
We do eventually. Do you think when they're far apart, President Cameron would send like a vice president to be on the other planet?
Ooh, probably. And it would probably be Kate Winslet. Because that's who he's casting.
Is Kate Winslet in Avatar?
Yes. She's in the new Avatar.
Oh, I have not seen the new Avatar.
Don't.
Okay. I'll take your word for it. Great. Thank you.
Well, also, I will emphasize, I watched Avatar at home, which means it did not have the sound quality, visual quality, or 3D experience that it was created to have, which means I'm watching it for the story, and the story is not it.
It's not it.
But yes, she is in Avatar, and she was also in Titanic.
Okay, so we have President Cameron on, do you think he's on planet E or F? Which is which is the capital?
E.
Yeah. Yeah. So President Cameron stays on E, and when they know that they're going to be separated, he sends Vice President Winslet to
with a script
to Planet F
for her for her to only follow the script for how to rule.
Eventually, though, they do actually have the like the avatar technology, so they can just have avatars on other worlds.
Exactly.
That was his campaign platform.
This is how he gathered the knowledge to like get the financial support to make the avatars. He's like, I just need $1 billion up front, and I swear over time I will release these movies.
I promise. Okay, great jobs, great candidates so far. We are on to our last election in 2014 of the president of Kepler 186f. This was the first Earth-sized planet to be found in the habitable zone of its star. Very exciting. Just one caveat. That star was not sun-like. It's an M-dwarf, about half the size and mass of the sun. The planet F orbits the star roughly once every 130 days. So it's like Earth, but redder.
Oh, okay. Let's think of redheads.
Oh.
Are there natural redheads in Hollywood?
Yes. There must be.
Emma Stone.
What about, like, Eddie Redmayne?
Oh, true, yes. I'm only thinking women for some reason.
I like that inclination. Let's lean into that for presidents.
Well, I love Amy Adams, but I don't know if she's a true redhead. If it's Earth-like but a little smaller, I feel like we're just going there to have fun, you know?
Yeah.
What if it's Britney Spears? Not a redhead.
Tell me more.
And I don't want to send her away, but I do think she would create like a really fun planet to live on. It would be weird, but like wouldn't be bad.
On Kepler 186f, I would vote for President Spears in a heartbeat.
Yeah.
She could serve infinite terms.
Yeah. She could film her little dances. She could just be her. Yeah. I think that might be it.
That's great. On Earth, I would not vote for her. On Kepler 186f, yes.
The stakes need to be 0.
I love that. Thank you for designing all of these campaigns. I will not ask you to be the campaign manager for all of them, but if you could choose just like 2 of your favorites, that would be great.
I'll make those posters and their taglines.
Okay. You did say at the top of the episode you wanted to know before the end why I like Kepler so much. I was resistant to doing exoplanet research for a very long time. My undergrad advisor was an exoplanet person, and I have pathological demand avoidance. So if there's an expectation that I will do something, I don't want to do it. But I found my way back to it over and over again once I gave it a try. And I love how intuitive the field of exoplanets is, especially transit photometry. It doesn't have as much of the complicated algebra and geometry and trig in it as like the radial velocity method, for example. So it's really intuitive. And as a science communicator, it's easier for me to get audiences to like relate to the transit method and exoplanets as a field. So I found it intellectually interesting. I found it very strategic for my science communication career. And I got so attached while I was doing my research to data coming from this little space machine that I'd never touched. And then when they announced the K2 mission, it was around the time that I was getting into astronomy in 2014. And so I was like, oh, that's interesting. They repurposed it. How creative and resourceful. And then when it retired in 2018, I was
in the thick of my PhD program and got really emotional
Yeah.
when it retired. So I've just been around Kepler specifically and exoplanets more broadly for a lot of the most important milestones of my career.
Yeah.
And they've never done me wrong.
I love that.
I love Kepler. I love you,
Kepler.
Yeah. But you don't have to be in love with a space-based telescope to remember that you are space. You already are.
You are. Bye.
Pale Blue Pod was created by Moiya McTier and Corinne Caputo with help from the Multitude Productions team. Our theme music is by Evan Johnston, and our cover art is by Shay McMullen. Our audio editing is handled by the incomparable Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Twitter and Instagram, or check out our website, palebluepod.com. We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
If you want to support Pale Blue Pod financially, join our community over at patreon.com/palebluepod. For just about $1 per episode, you get a shout out on one of our shows and access to director's commentary for each episode. The very best way, though, to help Pale Blue Pod grow is to share it with your friends. So send this episode, this link, to one person who you think will like it, and we will appreciate you for forever.
Thanks for listening to Pale Blue Pod. You'll hear us again next week.
Bye.